Cape, September 2015. Question 9. Learners conduct an experiment as shown in the diagram below. The results obtained are shown in the graph below. Okay. The graph has current on its y-axis and potential difference on the x-axis. We will use this equation I R multiplied by R. So we want to manipulate this equation so that it is a representation of the graph. So we have current on the y-axis and potential difference on the x-axis. EMF, we know that we must have potential difference. So this is V external, and we must have current somewhere. Then this is I multiplied by R. Okay, so let's fix this. So current must be on the y-axis. So I multiplied by R should be equals to the EMF minus V external. And then now we'll just divide by the internal resistance. So the EMF over R minus V external all over the internal resistance. V external is on the x-axis. That's where we have the potential difference. So let's fix this. So that's going to be 1 over R multiplied by V external plus 1 over R multiplied by the EMF. So now we have Y is equals to mx plus C. So on our y-axis we have the current. So it means that our gradient is the inverse of the internal resistance. On the x-axis we have V external, and then the y-intercept should be 1 over R multiplied by the EMF. So that's what we have, 9.1.1. Use the graph to determine the following. The EMF of the battery. The EMF of the battery is registered by the voltmeter when there's no current flowing in the external circuit. So the current is 0 at this point, and then the value of the potential difference is 1.5 volts. So it means that the value of the EMF should be equals to 1.5 volts. 9.1.2. We need to use the graph to determine the internal resistance of the battery without using that equation on our calculation. Okay. So the gradient should be the negative inverse of the internal resistance. Our gradient should be equals to the negative of our internal resistance. So this is the change in current over change in potential difference. When the current is 1.8, the voltage there is 0. And then when our potential difference is 1.5, the current is 0. So I'm getting negative 6 over 5. So now I just have to find the inverse. It's negative 5 over 6. Then I'm going to divide by negative both sides. So it's 0.83 ohms. So another way that we can look at this is option 1. For option 2, We know that the y-intercept is equals to the whole of that. So 1 over r multiplied by the EMF should be equals to the y-intercept. The y-intercept is at 1.8. So it should be equals to 1.8. The value of the EMF is 1.5. So we'll say 1.8 divided by 1.5. So we are getting 6 over 5. And then we're just going to find the inverse of the answer. So we are getting 0.83. 9.2. The resistance of the rheostat is now increased. How will this change the voltmeter reading? Write down increases, decreases, or remains the same. So we are increasing the resistance. When we increase the resistance, the current should decrease. An increase in resistance causes a decrease in the current. So now let's look at our graph. As the current decreases, our potential difference increases. So we expect the voltmeter reading to increase, because look, when you decrease the current, the voltmeter does what? It increases. So we expect an increase. 9.2.1. So this is increases. 9.2.2. Then we need to explain our answer. So we just say R external increases. Therefore, the current decreases. And then we'll just use this equation. So the current decreases. Since the value of the EMF doesn't change, V external should go up. Therefore, the external increases. 9.3. 4 identical cells, each with an EMF of 1.5 volts. So the EMF, the total EMF should be equals to 1.5 multiplied by 4, because we have 4 separate cells. So the total EMF should be equals to 6.0 volts and an internal resistance of 0.25. The total internal resistance should be 0.25 times 4. So we have an internal resistance of 1.0 ohms, are connected in series with each other and to the resistors as shown below. So this side is the positive terminal and that side is the negative. The total current will flow in this direction. That's I total. The current that passes through the 4 ohm resistor is the I total. At this junction, the current will be divided. So we'll have I1 and then we will have I2. At that point, the current combines again. So then we have I total. Write down the potential difference across the cells when the switch is open. So when switch S is open, there is no current flowing in the external. So the voltmeter will register the value of the EMF. So this is going to be 6.0 volts, 9.3.2. When switch S is closed, the potential difference across the 4 ohm resistor is equal to 2 volts. So we have 2 volts there. Calculate the current in the circuit. So that's the total current that's passing through the 4 ohm resistor. I should be equal to V over R. The voltage is 2 and then the resistance is 4. So that's 0.5 amperes. B. They want us to calculate Rx. Okay, I think we'll use 2 different methods to see if we get the same answer. So this is option 1. We have the EMF, we have the total current, we don't know the R external, but we do have the internal resistance. So this is 6 is equal to 0.5. R external, we don't know. The internal resistance is 1. Therefore, R external should be equal to so I am getting 11.0 ohms. The total resistance is, so we have something like that. So this is the 4 ohm, that's the 14 ohm, that's Rx. So the 14 ohm and Rx are connected in parallel. So the parallel combination should be, we find the product of the 2 resistance. So this is 14 Rx, and then we find the sum. So now we'll have something that looks like that. So this is R parallel, that's the 4 ohm resistor. So now we have a series combination. So R external should be equals to R parallel plus the 4 ohm resistor. R external is 11. The parallel combination is 14 Rx all over 14 plus Rx plus the 4 ohm resistor. 11 minus 4, that's 7. So 7 times 14, I'm getting 98 plus 7 Rx should be equals to 14 Rx. 98 should be equals to 7 Rx. Therefore, Rx should be equals to 98 divided by 7. So I am getting 14 ohms. That's option 1. Then for option 2, we can first find the external voltage, because we have the EMF V external, and then we have the total current as well as the internal resistance. The EMF is 6. V external we do not have. The current is 0.5. The internal resistance is 1. So V external should be equals to 6 minus 0.5. So I am getting 5.50 false. Okay, we have our circuit looks like this. Okay, so these two, the 14 ohm resistor and Rx, are connected in parallel, so they will have the same potential difference, but the current is going to be divided. So there we'll have I1 and this side will have I2. The potential difference should be the same. And then after I've combined the parallel combination, I'm going to have something like this. So this is 4 ohms and that's the parallel combination. For resistors connected in series, the potential difference that flows through here plus the potential difference that flows through the parallel combination, when I add the two of them, I must get V external. Okay, so V external should be equals to the voltage across the 4 ohm resistor plus the voltage that's in the parallel. V external is 5.50. The voltage through the 4 ohm is 2. V parallel. So I am getting 3.50 volts. That's the voltage across the parallel combination. So for the 14 ohm resistor, I know that the voltage must be 3.5 there. So I can find I1. The voltage is 3.50 and the resistance is 14. So I am getting 0.25 amperes. When we add I1 plus I2, we must get the total current. The total current is 0.50 and then I1 is 0.25 plus I2. The current through I2 should therefore be 0.25 amperes. Here you needn't even calculate Rx. You can just use the ratio. You can say I1 is equals to I2. So this means that Rx should be equals to 14 ohms as well, because the current is equally divided. This means that the resistance of Rx must be 14 as well. Or you can calculate it. And then you will say Rx should be equals to V all over I. The voltage there is 3.50 and this is 0.25. You should get 14 ohms.